Hi there, my name is Rebecca Weaver. We're going to be looking at section 3.3 today, Implicit Differentiation and Related Rates. That'll allow us to do some word problems. Now, for implicit differentiation, here's the general procedure for implicit differentiation. You're going to differentiate each term of the equation with respect to x, treating y as a function of x. Move all terms involving dy over dx, which is y prime, to the left side of the equation, and move the other terms to the right side. Factor out dy over dx on the left side of the equation. Divide both sides of the equation by the factor that multiplies dy over dx. Okay, that's the procedure. Let's see what in the world this is talking about. If we're to use implicit differentiation to determine the slope of the graph at the given point, here's what we need to do. The second term, notice this function is 4y cubed minus x squared equals negative 5. It's not a y equals thing. So the second term, x squared, has the derivative 2x, as usual. We know that. We can think of the first term, 4y cubed, as having the form 4 times g of x, the quantity cubed. To differentiate this, we're going to use the chain rule. So notice that our inside is our y there. Our outside is to the third power. So we're going to take the derivative of the outside. So we're going to bring my 3 down, multiply it by the 4, and get a 12. All leaving that inside alone, which is just a y, and then reduce that power times the derivative of that inside function. And the derivative of that would then look like 12y squared, and this g prime of x is just dy over dx. Now, on the right side of the original equation, the derivative of the constant function, negative 5, it's 0. Thus, the implicit differentiation of 4y cubed minus x squared equal 5 is 12y squared times dy over dx minus 2x equals 0. So what we want to do is get dy over dx all by himself. So we're going to move over the 2x and divide by 12y squared. So that's our process here. That's what we've done. And then we'll simplify, and we get that y prime, or dy over dx, is x over 6y squared. Now, that wasn't the question. The question said find the slope at a particular point, and they wanted the slope at the point 3, 1. So you'll just plug in a 3 for x and a 1 for y, and you'll get the slope at that point, or y prime, or dy over dx, is 1/2 when you simplify that. Now, the general power rule for implicit differentiation, just to make it easy, this is a rule to make it easier so that I don't have to always be thinking about that chain rule, is if I have some y to the r, it's just drop your power r, and then it'll be y to the r minus 1 times y primer times dy over dx. So let's look at an example. We need to use implicit differentiation to find dy over dx. And if you'll notice, I can't write it y equals because this 4x is all gunked in with this y. It's going to make it really difficult for this x squared plus 4xy plus 4y equal 1. And I want to know what dy over dx is. So here's our equation. We need to take the derivative of both sides with respect to x. I like the right side, that's easy. That's just going to be a 0. But then I need to take the derivative of x squared, the derivative of 4xy, and the derivative of 4y. So that's what we're going to be doing next. Then just taking those derivatives as they come. The first one, pretty easy, that's 2x, I've been doing that a while. This second one, not quite so easy, because that's going to involve the product rule. So I've got to do the product rule in this middle term. The second one, pretty easy because it just has the 4, and the derivative of y would just be dy over dx. So that one's okay. But this next one, I have 4xy. So if you'll remember that, so I'm going to write the 4x, take the derivative of the second, plus the second one, which is a y, times the derivative of first. So just times the 4x. All right, when I do that, I will get 2x plus 4x times y prime plus The derivative of 4x is just a 4, so that would be 4y plus 4y prime. So what I do is I just take anything that doesn't have a dy over dx in it and throw it all to the other side. So 2x and the 4y are scooting them little cells over. So you'll see them over there. Then I'll factor out this dy over dx. When I do that, I have 4x plus 4 times dy over dx. Divide both sides by the 4x plus 4, and you end up with this particular function, the negative 2x minus 4y all over 4x plus 4. Sure, that could you could take the 2 out of all of that if you wanted to make it a little simpler. Suggestions for solving related rate problems. My favorite, draw a picture if possible. That's the best thing to do. Assign letters to quantities that vary and identify one variable, say t, on which the other variables are all going to depend. Find an equation that relates the variables to each other. This is what we've been doing. Differentiate the equation with respect to the independent variable, say t. Use the chain rule whenever appropriate, of course. Substitute all specified values for the variables and their derivatives. Solve for the derivative that gives the unknown rate. Very typical example for related rates is when something is in motion, whether it be a plane, a car, it can be a bug, just anything that's moving with relation to another thing. So this one is an airplane flying 390 feet per second at an altitude of 5,000 feet. And it's flying directly over an observer. That's convenient. The figure below shows the relationship of the airplane to the observer at a later time. Now find an equation relating x and y. Find the value of x when y is 13,000. And how fast is the distance from the observer to the airplane changing? So how fast is basically this, let's see, the distance from airplane to, that would be the y directly. The x value would be just from above, but we want to know the actual distance, that dy over dx. How fast is that changing at a time when the airplane is 13,000 feet from the observer? That is, what is dy over dx at a time when the horizontal distance is changing at a rate of 390 and it's increasing. My y is holding steady at 13,000, and we're going to see how we're going to plug all of this stuff in. First up, we need to find an equation relating x and y. We notice that x and y are lengths of the two sides of a right triangle. Oh yeah, so let's use the Pythagorean. So we've got 5,000 plus x squared equals y squared. So just simplifying that a little bit, I got the 25 million plus x squared equals y squared. Love these big values. And that was all I needed to do for that question. So next I need to find the value of x when y is 13,000. That means I'm going to replace y with the 13,000. So just plugging that in, I'm going to get that my x squared is 144 million, and then I get that x is 12,000 when I take the square root of both sides. Cool. To determine how fast the distance from the observer to the airplane is changing at the time when the airplane is 13,000 feet from the observer, so that's when that y was the 13,000, we wish to determine the rate at which y is changing at this time. So we want dy over dx at this time. So we have the 25 million plus x squared equals y squared. And so we're wanting the dy, excuse me, I meant to say dy over dt. So there's our function there. We're going to take the derivative of all of this with respect to t. That means we're going to have, our constant is just 0, so we're going to have 2x, and then we have dx over dt equals 2y dy over dt. Now plugging in what we know that y is 13,000, x is 12,000 because we just found it, and then we know that the horizontal distance is changing with time at a rate of 390. Plugging all of these numbers in, then what we'll have to do is just solve for dy over dt. We get 360. This means the rate at which the distance from the plane to the observer is changing for the given values that we had specified is 360 feet per second. And that concludes our section 3 of chapter 3. So if you have any questions, be sure and email me, rweaver10@alaska.edu, and look forward to hearing from you. Have a fabulous day.